Today we're diving deep into some of the most profound questions about the extraterrestrial life. When did humans first consider the possibility of alien life? What is the historical background of the Fermi Paradox? How does the Drake equation estimate the number of civilizations in our galaxy? How is the Kardashev Scale used to classify alien civilizations? What is the Great Silence? Why are there no signs from alien civilizations? What is the Great Filter Hypothesis, and can we survive it? What is the Rare Earth Hypothesis? Is complex life uncommon in the universe? What is the Cosmic Quarantine Hypothesis? Is planet Earth a zoo for aliens? What is the Dark Forest Hypothesis? Are aliens intentionally avoiding contact with us? How could the James Webb Space Telescope detect signs of alien life? Is it only a matter of time before we find alien life? Let's delve into the answers to these questions with a comprehensive scientific perspective. When did humans first consider the possibility of alien life? The earliest theories resembling our concept of aliens trace back to the atomic theories favored by Epicurean thinkers in ancient Greece and their followers in Rome. Visionary thinkers like Democritus and Epicurus, gazing at the stars, theorized that countless other worlds were scattered across the cosmos, born from the random collisions of tiny atoms. These worlds, they believed, were likely bustling with life. One of Epicurus' followers, Metrodorus, argued that to think our planet was the only inhabited one was as absurd as expecting a single grain of wheat to stand alone in an endless field. Adding a poetic touch to this philosophy, the Roman poet Lucretius declared that in the vastness of the universe, no place was unique, suggesting that many other Earths, teeming with diverse peoples and creatures, must exist beyond our own. These early philosophers laid the groundwork for the concept of extraterrestrial life, a topic that still captivates us millennia later. Ancient Greek thinkers, such as Democritus and Epicurus, were ahead of their time, imagining the universe as filled with other worlds. However, their vision was different from ours. They didn't think of stars as other suns with planets like our own. Instead, they saw the stars as fixed points on a celestial sphere, separate from our world. The other Earths they contemplated were not neighboring planets, but distant, isolated realms, which in a way mirrors today's idea of multiple universes, vast, uncharted, and completely separate from our own existence. When we get to medieval times, the abstract musings of the Epicureans about countless inhabited worlds clash with the more grounded views of the Aristotelians, who valued observable reality over imagination. Aristotle's towering influence on the era's thinking pushed the concept of many worlds aside. Yet this idea wasn't entirely abandoned because Aristotle's assertion that multiple worlds couldn't exist was at odds with the Church's belief in God's limitless power. So while the notion of many worlds simmered on the philosophical backburner, it was kept alive by the very arguments used to dismiss it, waiting for a time when it could be rekindled and explored anew. The medieval theologians made it clear to scholars that Aristotle's rejection of multiple worlds was one stance they couldn't endorse as fact. This prohibition kept the door open for continued speculation and discussion about the existence of other worlds within the realms of academia. In the 15th century, the idea of extraterrestrial life gained new attention. Nicholas of Cusa argued that life exists throughout the cosmos, not just on Earth. He suggested that celestial beings of various ranks inhabit the stars and planets, all created by God. He posited that these beings would differ from us, with solar beings possibly being brighter and more spiritual, while lunar beings could be different, and those on Earth are more material. Yet, our understanding of these otherworldly inhabitants is limited due to our lack of comparative standards. Nicholas of Cusa's 15th century concepts departed from the idea of entirely separate universes as the Epicureans imagined. Instead, he envisioned a universe filled with life, including various forms of humans, animals, and plants on different celestial bodies, what we now would label as aliens. The concept of extraterrestrial life sparked intense debate among medieval theologians like Cusa's peers. They pondered profound questions. If such beings existed, did they fall from grace as humans did? Were they in need of redemption through Christ? William Vordelong, a French theologian, weighed in with his views. He believed that beings on other worlds had not inherited Adam's original sin offered by Christ's sacrifice on earth. Vorlong reasoned that its power was so immense it could extend across an infinite number of worlds. Yet, he found it inconceivable that Christ would have to suffer and die again on other worlds. So, medieval scholars didn't just muse about the existence of other inhabited worlds, but theologians also managed to fit these concepts into Christian beliefs, pondering how extraterrestrial life might align with humanity's cosmic role and the universal reach of Christ's salvation. The common view that the Middle Ages were a dark period, hostile to innovative thought, is challenged by evidence that scholars of the time did indeed engage with the notion of extraterrestrial life. This engagement did not always provoke accusations of heresy or endanger lives, suggesting a more nuanced intellectual climate than is often assumed. In this period, curiosity about the universe and its possible inhabitants was present, and there was room for debate and speculation about worlds beyond our own without the immediate threat of being branded a heretic or facing execution. This reveals a medieval scholarly world that was more open and inquisitive than commonly portrayed. Contrary to the perception of medieval heresy for unorthodox ideas, Nicholas of Cusa was esteemed for his work discussing extraterrestrial life. He was even appointed a cardinal and served as a papal legate. Similarly, William Vorlong, who contributed to the discourse, faced no heretical charges. In fact, Vorlong was known for his stand against the unjust trial of Joan of Arc, which he refused to endorse, criticizing it as an injustice. These examples illustrate that the medieval period was more intellectually diverse and less oppressive than often believed. In a nutshell, ancient and medieval intellectuals were fascinated by the idea of life beyond Earth, with early philosophers like the Greeks imagining separate worlds and later medieval thinkers considering the possibility of other planets in our universe being home to diverse forms of life. This intellectual journey marks the evolution from abstract speculation to more concrete hypotheses about extraterrestrial existence, blending philosophy, science, and even theology. What is the historical background of the Fermi Paradox? In conversations about the pursuit of extraterrestrial life, two major concepts often surface. The first is the Drake equation, a legitimate tool devised by the astronomer and SETI trailblazer Frank Drake. It provides an estimation, running into the thousands by some credible calculations, of the number of cosmic civilizations from which we might catch signals. The second concept is the so-called Fermi Paradox. This is a supposed argument suggesting that the presence of intelligent aliens should be evident to us through their interstellar colonization, if they truly existed. The paradox argues that because there's no clear evidence of such beings here, looking for their signals is futile. But this paradox is actually a misnomer. It's wrongly attributed to physicist Enrico Fermi, who in fact never made any such assertion. The Fermi paradox, often cited in debates over the existence of extraterrestrial intelligence, has been a point of contention and has impacted funding for related research. It played a role in the decision-making process of Senator William Proxmire, who argued for the discontinuation of NASA's SETI program in 1981. The program was briefly reinstated after advocacy from Carl Sagan, but was eventually terminated again in 1993 under Senator Richard Bryan. Following this, SETI initiatives within the United States have not been financially supported by federal funds, despite the discovery of numerous exoplanets orbiting stars. The Nobel laureate credited with constructing the initial nuclear reactor did not leave behind any published works on the topic of extraterrestrial life. Insights into his thoughts on the matter come from the work of physicist Eric Jones, who gathered written recollections from the three individuals present at a 1950 Los Alamos luncheon: Emil Konopinski, Edward Teller, and Herbert York, who outlived Fermi, who passed away in 1954. It is from this event that the concept widely referred to as the Fermi Paradox originated. Herbert York and Edward Teller's interpretations of Fermi's remarks indicate that his inquiry was about the plausibility of interstellar travel rather than a doubt about the existence of extraterrestrial life forms. Thus, the term Fermi Paradox, which casts doubt on the existence of extraterrestrials, doesn't accurately reflect Fermi's own position. His skepticism regarding space travel was congruent with the era's technological status, considering that in 1950, rocket technology had not yet succeeded in orbital launch, let alone reaching another planet or star. The pessimistic viewpoint that the absence of extraterrestrials on Earth equates to their non-existence didn't originate with Fermi, but was first proposed in print by astronomer Michael Hart in 1975. Hart suggested that the presence of intelligent aliens would naturally lead to the colonization of the Milky Way. From this, he argued that their non-appearance here on Earth implies that humans might stand alone as intelligent beings in our galaxy, leading him to view the search for extraterrestrial intelligence as a likely futile expenditure. This line of reasoning has faced various critiques, including the possibility that interstellar travel is unattainable, civilizations may opt against galactic colonization, or that aliens visited Earth in a prehistoric era, leaving no discernible traces. Despite these counterarguments, Hart's hypothesis has gained a foothold in the discourse on extraterrestrial life. In 1980, physicist Frank Tipler expanded upon Michael Hart's thesis by confronting a critical issue: the resource requirement for the colonization of billions of stars. Tipler's solution was the concept of a self-replicating universal constructor with human equivalent intelligence. This device could be dispatched to a nearby star, utilize local resources to create duplicates of itself, and then those duplicates could continue the process, potentially populating the entire galaxy. Tipler deduced that the non-existence of such advanced mechanisms on Earth is evidence that ours is the sole intelligent civilization in not just the Milky Way, but the entire universe. This is a substantial inference to draw from the simple fact that we have not encountered extraterrestrial beings on Earth. The core concept of what's often referred to as the Fermi Paradox is actually the brainchild of Hart and Tipler. Over time, their proposition has been mistakenly intertwined with Fermi's initial inquiry. This mix-up seems to have begun in 1977 with physicist David G. Stephenson, who applied the term Fermi Paradox in a publication, suggesting Hart's theory as an explanation to Fermi's question. A more precise label for this line of reasoning might be the Hart-Tipler argument against the existence of technological extraterrestrials. While it may not carry the same weight of authority as its misattributed predecessor, this rephrasing would be a more accurate homage to its true originators. How does the Drake equation estimate the number of civilizations in our galaxy? There is, as of yet, no definitive proof that interstellar voyages are achievable. Which notion is more astonishing? The existence of thousands of extraterrestrial civilizations actively existing in our galaxy at this very moment, or the prospect that we are the sole essence of life in this vast expanse. Ponder the scale involved. Our universe is awash with an unfathomable number of stars. Our own Milky Way, by the most conservative estimates, is home to 100 billion stars, and by more liberal accounts, up to 400 billion. Yet the Milky Way is but one galaxy among the countless others scattered across the cold, immense vacuum of space. Therefore, even if the odds of intelligent life forming are minuscule, the staggering quantity of stars overhead whispers the possibility that we are, in fact, not alone. A solitary figure who endeavored to unravel this stellar riddle was Frank Drake. He cataloged the series of queries that must be addressed by scientists to ascertain the tally of civilizations within our galaxy. He discerned that by combining these queries, multiplying them one by the other, the result would yield an estimate of the detectable civilizations. Hence, the inception of the now famed Drake equation. In the celestial tapestry of the Drake equation, our asterisk signifies the annual symphony of star creation within our galaxy. Proceeding forth, we encounter Phi, the segment of these luminaries that are centers of planetary systems. With planetary disks now spinning, the query arises: which of these worlds lie within the nurturing habitable zone? This segment of our cosmic puzzle is quantified by Ni, a value veiled by the vast unknowns of extrasolar planets. Potential abodes of life they may be, yet how many truly harbor it? This vital statistic is captured by Phi in the enigmatic Drake equation. Phi illuminates the number of hospitable planets upon which intelligence has dawned. Drake's vision was cast towards the realm of radio astronomy, his equation aspiring to capture the odds that extraterrestrial societies might reach out through detectable signals, a concept encapsulated by Phi. In the era of the 1960s, the consensus tilted towards radio as the beacon of choice for enlightened extraterrestrial civilization. Indeed, Earth itself has been casting a technological signature into the cosmos for the better part of a century. Within the radius of 80 light-years, a host of stars stand, each a potential sentry to life's whisper. Yet the question lingers, would other sapient entities across the stars still converse through radio waves, or might such a method be deemed as archaic by them as smoke signals are to us? Conceivably, there exists the chance that an alien society might intentionally shroud its existence from cosmic compatriots. It's plausible to argue that amidst the diversity of civilizations, some may not harbor friendly intentions. Thus, revealing one's cosmic coordinates could be an imprudent reveal. The concluding variable of the Drake equation carries with it a somber note. It seeks to measure the span for which a technological civilization remains observable. Encapsulated by L. Drake, harbored concerns that a sophisticated society might shine brightly yet fleetingly on the cosmic stage of detectability. It stands to reason that numerous civilizations, while they may prosper for eons, could only be within our perceptual reach for a transient phase of their extensive histories. What then is the solution? When Drake first performed his estimations in 1961, he deduced that the number of detectable civilizations in our galaxy would tally between 4 and 10. But if we refine Drake's parameters using contemporary scientific insights, a distinct picture emerges. The revised calculation for n is a scant 0.00127, suggesting that in any given 100,000-year epoch of our galaxy's saga, approximately 127 civilizations would emerge within the realm of detection. The belief that extraterrestrial societies are scattered throughout our galaxy was a cornerstone of Drake's work. His calculations led to the suggestion of a vibrant tapestry of approximately 10,000 civilizations in the Milky Way. Despite the vastness of this number, the daunting task of detecting even one amidst the at least 100 billion stars speaks to the immense challenge faced by astronomers. It implies a thorough search of 10 million stars is necessary before any skepticism about their frequency can be justified. How is the Kardashev Scale used to classify alien civilizations? Spanning over 13 billion years in age, the observable universe is a mind-boggling expanse hosting around 2 trillion galaxies, each brimming with an estimated 20,000 billion stars. Within just our Milky Way, scientists speculate the existence of some 40 billion planets akin to Earth, nestled in their stars' habitable zones. These astronomical numbers make it seem unlikely that Earth is the universe's sole cradle of life. Uncovering life elsewhere would irrevocably alter our cosmic perspective, showing us that this vast space is vibrant with existence. Such a realization could elevate our collective consciousness, helping us to overcome petty terrestrial squabbles. However, before we venture out into this cosmic quest for potential interstellar companions or adversaries, we face an essential quandary, defining the exact nature of what we're seeking in the universe's grand expanse. In a universe as vast and ancient as ours, it's logical to hypothesize that different civilizations emerge at intervals spanning millions of years, evolving along diverse not only immense distances, up to hundreds of thousands of light years, but also includes civilizations that could range from primitive to highly advanced. To enhance our search, we need a conceptual framework that allows us to think more effectively. Given that our only reference point is humanity, we must be cautious about making generalizations based on our singular experience. However, some insights can still be gleaned. Humans began with basic tools and a natural curiosity, driven by competition, a desire for resources, and a tendency towards expansion. These traits have been pivotal in the development of our civilization, leading to significant advancements. It seems plausible, then, to expect that extraterrestrial beings capable of dominating their planet might share similar characteristics. Additionally, if these alien species are bound by the same physical laws, then their technological progress could potentially be gauged by their energy consumption. This perspective provides a possible metric for assessing the advancement of extraterrestrial civilizations. Human advancement can be accurately tracked through our evolving ability to extract and utilize energy from our environment. Our journey began with the use of muscle power, progressing to mastering fire. We then harnessed kinetic energy from natural sources like water and wine through machines. With advancements in technology and material science, we tapped into the dense energy of fossil fuels. This escalation in energy consumption paralleled our civilizational capabilities. Building on these observations, scientist Nikolai Kardashev proposed a system to categorize civilizations based on their energy consumption, the Kardashev Scale. This scale, though refined over the years, primarily divides civilizations into four distinct levels. A Type 1 civilization utilizes the energy of its home planet. A Type 2 civilization harnesses the energy of its star and planetary system. A Type 3 civilization exploits the energy of its entire galaxy. And a Type 4 civilization extends its energy use across multiple galaxies. Each level on this scale represents a significant leap in complexity and capability, akin to the difference between an ant colony and a human city. To an ant, human structures and systems are so advanced as to appear godlike. To render the Kardashev scale more practical, it's beneficial to include subcategories for a more nuanced understanding of these vast differences in civilization development. On the Kardashev scale, civilizations between Type 0 and Type 1 cover a range from primitive societies to those comparable to what we might achieve in a few centuries. Such civilizations could be numerous in the Milky Way. However, without active radio signal transmissions into space, even a civilization in proximity, like in the Alpha Centauri system, could go undetected. Our own radio broadcasts, while covering 200 light-years, are a mere speck in the vastness of the Milky Way and degrade into indistinguishable noise after a few light-years. Presently, humanity is at about level 0.75 on this scale. We've significantly modified our planet, constructing massive structures, reshaping mountains, forests, and water bodies, and altering the atmosphere's composition and temperature. If we avoid rendering Earth uninhabitable, we could reach a full Type 1 status in the coming centuries. Reaching this stage implies a natural progression towards exploration and exploitation beyond Earth, fueled by our innate curiosity, competitiveness, and expansionist nature. The pathway to becoming a Type 2 civilization involves extensive space endeavors. It might start with space outposts, evolving into space-based infrastructure and industries, leading to colonies, and eventually terraforming other planets. As a civilization's activities and resource consumption expand, so does its energy needs. A significant milestone for an emerging Type 2 civilization would be constructing a distant swarm around their star, providing nearly unlimited energy for vast system-wide projects. With such capabilities, the ambition of a Type 2 civilization would naturally extend to other star systems, analogous to how we view the distance to Pluto today, challenging yet attainable with considerable effort and resources. This marks the beginning of their evolution towards a Type 3 civilization. The challenges at this stage, like traversing immense distances and maintaining cultural and biological coherence across light years, are difficult for us to fathom. It raises questions about whether such a civilization could overcome the vast travel times, preserve a unified identity across distant colonies, or if they would diverge into distinct civilizations. Type 3 involves navigating not just physical distances, but also potential existential risks lurking in the interstellar void. As a civilization advances towards a Type 3 status on the Kardashev scale, imagining their form and nature becomes increasingly challenging. Such civilizations might uncover novel physics principles, master dark matter and energy, or even achieve faster-than-light travel. Their motives, technology, and actions could be beyond human comprehension. In this scenario, we humans are akin to ants trying to decipher a galactic metropolis. To a highly advanced Type 2 civilization, humanity might appear too rudimentary for interaction, while a Type 3 civilization could regard us as we do bacteria on an anthill, possibly disregarding our consciousness or survival as inconsequential. To such entities, we could only hope for benevolence. However, the scale might extend even further. Some theorists propose the existence of Type 4 and Type 5 civilizations, wielding influence over galaxy clusters or superclusters, encompassing thousands of galaxies and trillions of stars. The pinnacle of this scale is the hypothetical Type Omega civilization, capable of manipulating the entire universe and perhaps even creating universes. Despite the speculative nature of this classification, it offers intriguing insights. If our assumptions about interstellar civilizations are somewhat accurate, then it's highly unlikely that Type 3 or higher civilizations are near the Milky Way. Their presence would be unmistakable, with clear signs of their activity across numerous star systems. The absence of evidence like harvested stars, decaying megastructures, or remnants of interstellar conflicts suggests they do not exist nearby. This realization, while somewhat disheartening, also provides reassurance. It implies that the galaxy remains open for humanity and civilizations similar to ours. The most likely extraterrestrial civilizations to discover would fall between Type 1.5 and Type 2.5, advanced enough to be intriguing, but not so advanced as to be incomprehensible. These civilizations might be engaged in constructing megastructures, traveling between stars, and possibly sending vast amounts of information into space. Yet, it's possible that our understanding of progress towards Type 2 is limited, and humanity's outward expansion mindset might be a reflection of our current developmental stage. For now, our search for extraterrestrial life is in its infancy. Until we encounter advanced alien civilizations capable of elucidating the mysteries of the universe, we are left to our own devices in unraveling the secrets of the cosmos. What is the Great Silence? Why are there no signs from alien civilizations? Why does a haunting silence greet our search for extraterrestrial life in a universe so immense, filled with countless stars and myriad planets? This perplexing phenomenon, known as the Great Silence, implies a vast universe devoid of detectable signals or signs from alien civilizations, challenging our understanding of the seemingly boundless cosmos. In 1967, Jocelyn Bell, a postgraduate student at Cambridge University, was conducting sky surveys using a new radio telescope. She detected a peculiar radio signal that pulsed regularly every 1.33 seconds. Initially dismissed as human-made interference, it soon became evident that this signal originated from deep space. Its consistent timing was unlike anything previously observed, leading to speculations about extraterrestrial origins. The source was humorously named LGN-1, short for Little Green Men, reflecting the initial wonder about alien communication. However, the mystery was soon resolved as a natural phenomenon. The signal was from a pulsar, a type of rapidly spinning neutron star emitting radiation beams, similar to a lighthouse's light beams. This discovery, while debunking the alien theory, sparked a global initiative known as the Search for Extraterrestrial Intelligence, which seeks artificial transmissions from space. Despite extensive efforts, no definitive extraterrestrial signals have been found. Humanity has been inadvertently sending radio signals into space for around a century. These signals create a radio bubble extending about 100 light-years from Earth, potentially alerting extraterrestrial civilizations within that range. Beyond this bubble, Earth's presence is virtually undetectable. Additionally, as technology advances, Earth's unintentional radio emissions are decreasing, potentially leading to a future of radio silence. The brief lifespan of a civilization's radio signals in the cosmic timeline poses a challenge as they travel through space. Military radar signals are among the strongest leaks into space, having a higher chance of detection over vast distances than standard TV broadcasts. The Square Kilometre Array, an upcoming large interferometer in South Africa and Australia, might detect faint signals from Earth-like civilizations up to several hundred light-years away. Deliberate communication attempts, such as the 1974 Arecibo message sent from Puerto Rico towards a distant star cluster, offer a more focused approach. However, these efforts are fleeting, giving extraterrestrial observers a small window to detect them. An example of a potential extraterrestrial signal is the 1977 WOW signal, a brief burst of energy that was never conclusively explained or detected again. Ultimately, the likelihood of two civilizations coincidentally discovering each other by randomly broadcasting is slim. To increase our chances of contact, we need to target our searches more strategically, focusing on signs of technological and biological life in the cosmos. In 1995, astronomers made a groundbreaking discovery: the first planet orbiting a star similar to our Sun outside our solar system. Since then, we've learned that most stars in our galaxy likely have at least one planet, with billions resembling Earth in size and orbiting in their star's habitable zone. This zone allows for the possibility of liquid water, a crucial component for life as we know it. Even moons orbiting these extrasolar planets might support life, with estimates suggesting there could be as many as 1 billion such moons. Recognizing this potential for extraterrestrial life, in 2017, a targeted message was sent to one of the most Earth-like exoplanets we've discovered, which is relatively close to us. This message included musical pieces and information about humanity. If the planet is inhabited and capable of responding, we might receive a reply by 2044. Determining if a planet actually harbors life involves detailed examinations, such as analyzing the chemical composition of an exoplanet's atmosphere. This is done by observing the starlight that passes through it. For example, an atmosphere rich in oxygen, similar to Earth's, might suggest the presence of life, as on our planet oxygen is largely produced by photosynthetic organisms. However, the presence of oxygen alone isn't conclusive, as it can also be produced by non-biological processes. Astrobiologists are particularly interested in specific chemical combinations that are unlikely to coexist without life, such as methane and carbon dioxide. Additionally, chemicals like carbon dioxide could indicate industrial activity and climate change, serving as a sign of intelligent life. Beyond biosignatures, we might detect technology-related indicators, or technosignatures. For example, an exoplanet with a dense belt of artificial satellites or space debris could be identified when it transits its star. Theoretical constructs like Dyson spheres, proposed by physicist Freeman Dyson, are another example. These hypothetical megastructures would be built by advanced civilizations to capture a star's energy. The Kardashev Scale, proposed by astrophysicist Nikolai Kardashev, categorizes civilizations based on their energy consumption. A Type 1 civilization uses its planet's energy, Type 2, its star's energy, and Type 3, the energy of an entire galaxy. While there's no confirmed evidence of Type 2 or 3 civilizations in the Milky Way, such concepts drive our search for extraterrestrial intelligence. Finally, curious astronomical phenomena sometimes spark alien-related speculations. For instance, a distant star, known for its irregular dimming, once led to theories about alien megastructures blocking its light. However, this is now thought to be caused by dust, not extraterrestrial engineering. Despite these speculative discussions, the search for concrete evidence of extraterrestrial life continues. The quest for extragalactic life, particularly advanced civilizations, continues to intrigue astronomers. Despite extensive surveys of 100,000 galaxies for evidence of a Type 3 civilization, which would command the energy of an entire galaxy, no signs of such a galactic empire have been found. This vast silence in the universe raises questions, especially since Earth itself has been emitting detectable biosignatures for about 1 billion years without attracting apparent attention from alien civilizations. This discrepancy between the high probability of extraterrestrial life and the lack of evidence for it is known as the Fermi Paradox. One possibility is that life, especially intelligent life, is extremely rare. Earth's history shows a lengthy evolutionary process with several mass extinctions before humans evolved. This hypothesis argues that complex life on Earth resulted from a series of unlikely events, possibly unique in the universe. There might be a great filter, a significant barrier to the development of life. If this filter lies in the past, Earth might be among the few that crossed it. If it's in the future, humanity might face an existential threat leading to its end. The nature of alien life is another area of speculation. Life on Earth is carbon-based and water-dependent, but extraterrestrial life might be fundamentally different, such as silicon-based life forms in ammonia oceans. This diversity could lead to us missing signs of alien life because we are searching for life as we know it. There's also the possibility that advanced civilizations evolve beyond physical reality. The transcension hypothesis, proposed by futurist John Smart, suggests that advanced civilizations might turn inward, focusing on creating hyperrealistic simulations and exploring virtual worlds rather than the physical universe. Such civilizations could eventually reach a point where their technology miniaturizes to a scale analogous to black holes, effectively disappearing from the observable universe. In the search for extraterrestrial intelligence, artificial transmissions and signs of astroengineering remain key. For example, launched in 1977, Voyager 1 and Voyager 2 stand as cornerstones in the human quest to reach out to extraterrestrial intelligence. These twin spacecraft, each equipped with a golden record, carry detailed information about humanity and the diversity of life on Earth. This makes them not only explorers of the cosmos but also emissaries, bearing messages intended for any potential extraterrestrial civilizations they might encounter. Voyager 1, destined to drift among the stars, is on a 40,000-year journey to approach another star system. In contrast, Voyager 2, following a different path, has provided invaluable insights into the outer planets of our solar system and entered interstellar space in 2018. As they journey through the vastness of space, these probes embody our deep-rooted curiosity and our ongoing efforts to understand our place in the cosmos, while their transmissions back to Earth enrich our knowledge of the universe. This advancement in technology leads to a perplexing question. Why does our solar system appear devoid of such probes? If the rate of human technological progress is any indicator, the galaxy might be expected to be teeming with self-replicating automatons, yet there is no evidence of this. Searches for alien artifacts in our solar system haven't yielded any confirmed findings, but the vastness of space means that extraterrestrial objects could easily evade detection. In 2017, an object from beyond our solar system, named Oumuamua, passed through the inner solar system undetected until it was on its way out from the Sun. Its discovery was a stroke of luck, suggesting that many such objects could pass unnoticed. Oumuamua's peculiar shape and behavior, initially classified as a comet, then reconsidered due to its lack of a cometary coma and unexpected acceleration, sparked debates about its nature, including the possibility of it being an interstellar probe potentially propelled by a light sail. However, Oumuamua remained radio silent, akin to a defunct probe wandering the galaxy much like Voyager. Our understanding of life in the universe is limited by our singular example, Earth. The discovery of life elsewhere, even within our solar system like beneath Europa's ice, would provide invaluable insights into the prevalence of life in the cosmos. The quest to solve the enigma of the Great Silence has seen remarkable advancements in recent years. The James Webb Space Telescope, launched in 2021, revolutionized the study of exoplanet atmospheres, enhancing our ability to detect potential signs of life. Breakthrough Listen, an ambitious initiative, expanded the search for extraterrestrial intelligence using more sensitive detection methods. The increased observation of Oumuamua-like interstellar objects has intensified discussions about their origins, whether natural or artificial. On Mars, the Perseverance rover's 2021 landing marked a significant step in the search for biosignatures, deepening our insights into the possibilities of life within our solar system. Furthermore, the field of astrobiology is actively exploring the potential for life in extreme environments, broadening the horizons of our search for extraterrestrial life forms. These efforts represent a growing commitment to unraveling the mysteries of the cosmos, acknowledging that discovering extraterrestrial life would be a monumental milestone in human history. Many scientists challenge the view of Earth as a unique cosmological entity, given the vast number of Earth-like planets and the tenacity of life on Earth. However, the actual probability of life, particularly intelligent life, the conditions necessary for abiogenesis, the transition from non-life to life. Asserting our solitude in the universe without more evidence is premature. Our search for extraterrestrial intelligence has been limited, akin to searching for fish in a glass of water when compared to the enormity of the oceans. Space is immensely vast, and our exploration has just begun. There are numerous unexplored methods for detecting life. By adjusting our telescopes, expanding their size, and tuning into different frequencies, we might find that the universe is not as silent as it currently seems. What is the Great Filter hypothesis, and can we survive it? Space exploration is one of humanity's most remarkable achievements, with more exciting discoveries on the horizon. However, there's a looming question. Could all this progress be halted by an existential threat? The universe might eventually reveal a harsh truth to humanity, the unavoidable end that awaits all life. This brings us to the Great Filter theory. It proposes that every intelligent civilization will encounter seemingly unbeatable challenges at some point, leading to their inevitable decline without leaving any lasting evidence of their existence. Economist Robin Hanson introduced the Great Filter hypothesis in 1996 as a way to explain the Fermi Paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of evidence for or contact with such civilizations. Hansen theorized that the emergence of intelligent life might be extremely rare. This rarity could be due to unknown scientific factors that prevent life forms from evolving into advanced civilizations capable of cosmic exploration. If this hypothesis holds true, it implies that humanity might also face such insurmountable obstacles, potentially leading to our own eventual extinction. The Great Filter concept proposes potential barriers to the evolution of intelligent life. These barriers could have occurred in the past, preventing animals from evolving into intelligent beings, or they might lie in the future, posing a significant risk of self-destruction for any advanced civilization. This theory suggests that the smoother the evolutionary process has been up to now, the more daunting the future challenges for humanity might be. Essentially, if we haven't encountered our Great Filter yet, it's likely that we will face it eventually. Initially, this hypothesis was received with skepticism. The smooth evolution of species on Earth implies that similar conditions could exist elsewhere, potentially leading to other intelligent life forms. The Drake equation, which estimates the number of advanced civilizations in the Milky Way, supports this idea, suggesting the existence of several dozen such civilizations. These civilizations might have developed technologies like radio astronomy or spacecraft similar to our Voyager probes, making interaction with an alien civilization seem plausible. However, despite our efforts to find extraterrestrial intelligence, the universe has yet to reveal any sign of it. This absence of evidence could be explained by the Great Filter, which might be the reason we haven't found any clues of other intelligent life forms in the vast universe. The Great Filter hypothesis posits that advanced civilizations must navigate one or more critical challenges during their evolution. The existence of such filters could explain why we haven't detected signals from other advanced civilizations in the universe. The hypothesis allows for the possibility that some species may overcome the Great Filter by progressing through several key stages. Initially, a habitable planet within its star's Goldilocks zone is necessary. Life must then emerge and evolve, utilizing complex molecules like DNA and RNA for reproduction. The transition from single-celled to complex multicellular organisms is crucial, as is the development of sexual reproduction to enhance genetic diversity. This evolution should lead to sophisticated organisms capable of tool use and technological development, eventually reaching a level advanced enough for space colonization. The final goal is to colonize other planets and star systems to prevent self-destruction. Robin Hanson suggests that only after achieving space colonization can a civilization consider the Great Filter as a challenge of the past. At our current evolutionary stage, humanity faces the daunting task of colonizing other celestial bodies for survival. Hanson argues that an intelligent species encounters a critical, potentially species-ending obstacle could lead to the total elimination of the species. Humanity may have completed 8 of these steps, but the likelihood of successfully navigating the 9th, which involves space colonization, is uncertain and may represent the fatal challenge that could lead to our extinction. The Great Filter hypothesis outlines several factors that civilizations must address to avoid self-destruction, including preventing internal wars, mitigating irreversible environmental damage, and conserving natural resources. This line of thinking is not just theoretical, but could also guide our space exploration strategies. According to this theory, finding extinct multicellular life on Mars, for instance, would be concerning. It would suggest that the evolutionary stages we've passed so far might have been the easier ones, with more formidable challenges yet to come. The simpler the evolutionary process on other planets, the less likely it is that humanity will become a spacefaring civilization. However, the situation is not entirely pessimistic. It's possible that humanity has already overcome the most significant hurdle in its evolutionary path. Thus, some scientists argue that our apparent solitude in the universe might be a positive sign, indicating that we've successfully navigated through the Great Filter. Nonetheless, it's important to recognize that we use only a few forms of communication, while others may exist. Considering the universe's estimated 13.8 billion year existence, many organisms might have surpassed similar challenges. Yet, they remain unaware of each other due to the need for significant technological advancements, which could ironically lead to their downfall. This is exemplified by Earth, where our technological progress has brought us to the brink of potential self-annihilation through nuclear war. The likelihood that our civilization could be destroyed before developing more advanced propulsion or communication technologies is significant. Identifying the Great Filter is challenging, as conditions on other planets may vastly differ from Earth's. Abiogenesis, the transition from inorganic to organic matter, is a complex process that might be the Great Filter for many intelligent species. Considering the Great Filter hypothesis, it raises significant questions about humanity's future. Will we be capable of effectively overcoming an unforeseen challenge, or have we already passed the most difficult phase? Is the universe's silence an indication that we are among the rare species to have successfully navigated all the stages set by the Great Filter? Regrettably, these questions remain unanswered at present. Our only option now is to prepare ourselves for whatever trial or challenge the universe might present to us. What is the rare Earth hypothesis? Is complex life uncommon in the universe? It's quite remarkable to think about how we exist in one of the rare spots in the universe where life is possible, where we don't instantly suffocate, freeze, burn up, or dehydrate. It's almost as if we're extraordinarily fortunate. This unique position we have on Earth, comfortably situated in its biosphere, offers us a special viewpoint on the universe. This perspective could even provide insights into the Fermi Paradox. It makes sense that we inhabit a planet capable of supporting our life, and a universe that has the capacity to create such planets. The anthropic principle suggests that it's no coincidence we find ourselves here. There's an inherent observer bias. The strong anthropic principle proposes that any universe we observe must have the conditions necessary to produce observers like us. We'll explore the implications of this idea, including the controversial suggestion that it hints at the existence of other universes. However, our current focus is on the weak anthropic principle. Despite its name, it's quite significant. It asserts that we must exist in a part of the universe that can sustain us, like a planetary biosphere rather than in the inhospitable emptiness between galaxies. While this may seem obvious, acknowledging this observer selection bias is crucial for understanding why the universe appears as it does from our vantage point. The weak anthropic principle, when considered alongside the noticeable absence of extraterrestrial civilizations, could suggest that intelligent life is extraordinarily scarce in our universe. To understand this, consider the nature of these questions as a unique mental experience, which you are undergoing right now. This kind of consciousness, your specific type of existence, might be exceedingly rare or even one of a kind, only possible in highly specific environments. Yet you are experiencing this consciousness, embodying it. Regardless of how infrequent such life-supporting environments may be, you inevitably exist in one of them. The weak anthropic principle does not limit the scarcity of these environments. For instance, if there's only one planet with life in the galaxy, or even in the entire universe, it's the one you would inhabit. This leads us to the rare Earth hypothesis, which argues that a multitude of unique factors makes Earth an exceptionally rare and ideally suited planet for fostering intelligent life. This hypothesis is supported not just by remarkable characteristics of our planet, which will be discussed, but also by the noticeable absence of alien life. The Fermi Paradox highlights the contradiction between the vast number of potential sites for life in the galaxy and the clear lack of evidence for other galactic civilizations. We've explored the Fermi Paradox and its possible explanations before, but let's consider the idea that the paradox is exactly as it appears. Technological civilizations are extremely rare, possibly because planets like Earth are exceptionally uncommon. The Fermi Paradox often leads to discussions about the Great Filter concept, which involves highly challenging or improbable steps in the evolution from a lifeless planet to a technologically visible civilization. One potential filter could be an impending danger, such as climate change or nuclear annihilation, that might still threaten to eliminate us. However, The rare Earth hypothesis offers a somewhat more optimistic view, suggesting that planets capable of developing civilizations like ours are exceedingly rare. This idea was popularized by Peter Ward and Robert Brownlee in their 2000 book, focusing on the unique characteristics of Earth necessary for life and intelligence to emerge. Before delving into Earth's unique qualities, it's worth noting what's not rare about Earth. Earth-like planets are quite common. These are rocky planets, similar in size to Earth, orbiting sun-like stars at a distance where liquid water can exist, the habitable or Goldilocks zone. The Kepler mission indicated that there could be around 10 billion such planets in our galaxy, and possibly 40 billion if we include planets around other types of stars. With billions of potential cradles for life in the Milky Way, even if just one civilization had a slight head start over us, it could have colonized the galaxy by now. This leads to the idea that Earth might possess unique qualities, making true Earth-like planets much less common than we think. Considering Earth's unique characteristics essential for life, we can gauge their rarity. If any other planet shares a life-critical feature with Earth, that feature might be relatively common. However, if a feature is only observed on Earth, it could be extremely rare. According to the weak anthropic principle, it's not surprising that we are on one of the few planets possessing these unique qualities. Currently, our knowledge of exoplanets is limited, so we'll compare Earth with the other rocky planets in our solar system. Two distinct qualities set Earth apart. 1. Its dynamic interior, and 2. Its large moon. The core of the Earth consists of a solid iron inner core within a molten metal outer core. The movement within this core generates a powerful magnetic field, shielding Earth from harmful space radiation and solar storms. Above the core is the solid, yet flowing, mantle which drives plate tectonics. The Earth's crust is divided into plates that float and periodically sink back into the mantle, a process known as subduction. This tectonic activity not only leads to ecosystem changes but also promotes biodiversity through environmental shifts. The recycling of nutrients from the Earth's crust into the mantle and back into the atmosphere through volcanic activity is vital for maintaining a rich biosphere. In contrast, Mars lacks significant tectonic activity, and Venus, if it has any, is limited, with neither planet boasting a protective geomagnetic field. While we can't be certain about the frequency of tectonic activity on exoplanets, it might be a rare phenomenon. Earth's moon stands out as exceptionally large compared to those of other rocky planets in our solar system, a characteristic that may be incredibly rare on a galactic scale. Its size, composition, and orbit indicate it likely formed from the debris of a colossal collision between a Mars-sized planet and the early Earth. This event could have been pivotal for life's development on Earth, possibly have accelerated Earth's rotation, resulting in shorter nights vital for photosynthesis and establishing Earth's axial tilt. A moderate tilt is potentially crucial for life, as it creates seasons that are not too extreme. Earth's tilt appears to be in a Goldilocks zone, possibly a rarity. The impact may have also initiated Earth's tectonic activity by fragmenting its early crust. Additionally, the moon's tidal effects might have enhanced ongoing tectonic movements. Another theory suggests that the moon played a role in abiogenesis. The hypothesis posits that life began in tidal pools, where the moon's gravitational pull created conditions favorable for the emergence of complex chemicals and protocells. Furthermore, our entire solar system is quite unique. The Kepler mission's findings on other planetary systems highlight this uniqueness. Our solar system features a wide variety of planet types, ranging from small rocky planets like Mercury to large gas giants like Jupiter and Saturn. This diversity is unusual compared to other systems, where planets tend to be more uniform in size. Large planets like Jupiter and Saturn are rare, found in only about 10% of systems. Jupiter, in particular, may have played a crucial role in life's development by acting as a cosmic shield. Its strong gravitational pull likely captured many comets and asteroids that could have otherwise collided with Earth, preventing numerous mass extinction events and potentially allowing for the uninterrupted progression of life and evolution. Several other factors might contribute to Earth's uniqueness, including a particularly conducive atmosphere and water abundance, as well as our planet's fortunate escape from cosmic disasters like gamma-ray bursts. However, what could truly set Earth apart in the cosmos is the unique trajectory of its evolutionary history. Life, especially in its simplest form, might be widespread, but the transition from single-celled to complex life, or the development of intelligence, could involve extremely rare evolutionary steps. One notable instance is the formation of the eukaryotic cell, which appears to have been a rare evolutionary event where two simpler cell types merged, with one cell becoming the mitochondria. This fusion dramatically increased the complexity of the cell, leading to multicellular life. There have been numerous critical junctures in Earth's evolutionary history, such as the Cambrian explosion, the asteroid that caused the dinosaurs' extinction, or other potential events that could have drastically altered the course of life. Earth seems to have been fortunate in its evolutionary journey. The rare Earth hypothesis questions just how much luck played a part in our planet's development. Many of Earth's life-supporting characteristics and evolutionary milestones seem unique or singular events. According to the weak anthropic principle, these events could be incredibly rare. We can't assume they are likely until we find more evidence, ideally by observing them elsewhere or happening again. The combination of these highly improbable factors might make intelligent life exceedingly rare. The solution to the Fermi Paradox could be that the galaxy is as barren as it appears. We might indeed be in the only viable location, looking out from our rare Earth into the vast, uninhabited expanse of the universe. What is the cosmic quarantine hypothesis? Is planet Earth a zoo for aliens? The Fermi Paradox, which highlights the contradiction between the high probability of extraterrestrial life and the lack of contact with such civilizations, has led to various intriguing theories, including the zoo hypothesis. This hypothesis posits that while alien life exists, it intentionally remains hidden, treating Earth and possibly other planets as sanctuaries. The key question here is why these advanced beings would go to such lengths to remain concealed. One possible scenario under this hypothesis is the risk of interplanetary contamination. Just as we fear Earth microbes contaminating other planets, aliens might also be concerned about their organisms disrupting Earth's ecosystem. To prevent this, they might observe us from a distance, avoiding any direct contact to maintain ecological balance. The challenge in understanding and communicating with alien civilizations also plays a role. Due to the vast differences that might exist between species, interactions could be confusing or futile. Hence, aliens might prefer to study us covertly, maintaining their anonymity to avoid misunderstandings. Watchers is another aspect of the zoo hypothesis, where extraterrestrials observe Earth passively. This could be for scientific study or to allow human civilization to evolve without external influences. Alternatively, it could be a strategy to monitor without engaging, especially if they consider us too primitive for direct contact. Another interpretation suggests that our perception of no alien contact might be due to differences in timescales. Aliens could be visiting Earth every few thousand or million years, making their presence so infrequent and brief that it leaves no lasting evidence. The slow reveal theory within the zoo hypothesis suggests that a sudden introduction to an advanced alien civilization could have disastrous effects on humanity. Therefore, these extraterrestrial beings might choose a gradual approach to reveal their existence, allowing us to adapt slowly to the reality of their presence. Ancient taboos among alien cultures, such as a prohibition against initiating contact with less advanced civilizations, might also explain the lack of contact. This could stem from the practices of a dominant ancient civilization in the galaxy, setting a precedent followed by younger civilizations. To minimize risks in first contact, advanced aliens might only intervene in our development when absolutely necessary. They could be aware of potential technological dangers that we are yet to fully comprehend and might choose to observe silently, intervening discreetly to avoid large-scale disruptions. The preservation hypothesis considers the importance of maintaining cultural and technological diversity. Too much interaction between civilizations could lead to a loss of uniqueness, prompting civilizations to remain isolated and only observe from a distance. Cultural unknowns like xenophobia or religious beliefs in alien societies could also drive the dynamics of the zoo hypothesis. These cultural norms might lead to long periods of isolation or unpredictable behaviors in response to certain cosmic events. A more sobering theory is the possibility that intelligent life is extremely rare or even non-existent beyond Earth. This could be a natural occurrence or the result of a dominant civilization suppressing the emergence of other intelligent beings. Alternatively, the universe itself could be a simulation, with Earth as the focal point. Lastly, the laboratory hypothesis suggests that our universe might be a controlled environment, designed by unknown forces. This aligns with the idea that the universe seems perfectly tuned for life, potentially as part of an elaborate experiment. These various aspects of the zoo hypothesis offer different perspectives on why we might not have encountered extraterrestrial life, each providing a unique answer to the enigma posed by the Fermi Paradox. What is the dark forest hypothesis? Are aliens intentionally avoiding contact with us? The vastness of the universe with its countless habitable planets suggests a high potential for extraterrestrial life. The Fermi Paradox highlights this contradiction. If even one advanced civilization had the capability to traverse the stars at a mere 0.1% the speed of light, it could spread across our galaxy in about 100 million years, a brief span in the context of the Milky Way's multi-billion-year history. This suggests that spacefaring civilizations could quickly occupy large sections of the galaxy. Yet, the universe appears silent and empty, with no signs of other life forms. This apparent emptiness poses a stark dilemma for humanity, caught between the desire to find others in the Milky Way and the fear of what revealing ourselves might bring. This leads to the dark forest theory as a possible explanation for the Fermi Paradox. It suggests that the universe might indeed be teeming with civilizations, but they choose to remain hidden from each other. The history of Earth's own life forms underscores this caution. Living beings inherently compete for survival, resources, and reproduction. This competition has historically favored those with advantageous traits. Human ancestors, characterized by their inventiveness, competitiveness, and resourcefulness, emerged victorious in this planetary competition, leading to a dominance so profound that our activities inadvertently cause the extinction of numerous species daily. Thus, in a universe where every civilization is striving to survive and expand, revealing oneself might be a dangerous move, akin to a lone hunter in a dense, foggy forest, hesitating to call out, aware that others like him might be lurking in the shadows. Humans are not just solitary beings. We form cultures that engage in their own form of competition. Cultures that are competitive and expansionist tend to spread more rapidly, often assimilating, subjugating, or eradicating other cultures. Humanity is a threat, not only to other species but to itself. Driven by our nature, we've occupied every corner of Earth and are now turning our gaze to the stars, seeking new realms and resources. It's probable that this competitive drive is not unique to Earth, suggesting that an alien civilization that has conquered its own planet may share similar traits to humans, including potential danger. As a lone hunter moves cautiously through a dark, dense forest, he is aware that others like him might be out there. Unable to discern their intentions, and knowing he would act aggressively for survival, he must assume they would too. This scenario could mean that in a chance encounter, preemptive action might be a survival tactic. However, this doesn't imply that conflict is inevitable. Modern human progress seems to have made us more peaceful. This trend could be true for other civilizations, where advancement leads to less conflict. Alien civilizations could range from benign and peaceful to hostile and militaristic. The crux of the issue in interstellar encounters is the uncertainty of intentions. We cannot easily discern whether an alien civilization is peaceful or aggressive, just as they might misinterpret or distrust our peaceful overtures. This ambiguity poses a significant existential challenge when meeting others among the stars. Furthermore, discovering an alien civilization and being discovered in return introduces the challenge of communication delays spanning years due to the vast distances of light years. This delay breeds uncertainty, raising the question of whether preemptive attack is the safest strategy. This concern is exacerbated by the unpredictable pace of technological advancements and the concept of first strike advantage. Technological progress has always been a decisive factor in warfare. A gap of a few centuries could transform a balanced conflict into a one-sided annihilation. Historical examples, from Caesar's legions to modern drones and guided missiles, illustrate how advancements can render previous military technologies obsolete. In the realm of interstellar conflict, the time it takes to send an invasion fleet across light years means that by the time it arrives, it may be outdated. Thus, wars between civilizations might revolve around eliminating the other as an existential threat. The fear that the other might attack first could prompt a preemptive strike. The most effective strategy in such a scenario would be an overwhelming and rapid assault, leaving no opportunity for the target to retaliate or escape for future revenge. The high stakes allow no margin for error. Assuming most civilizations are planet-based makes them vulnerable to massive planet-destroying weapons. One example is the relativistic kill vehicle, a missile traveling at a significant fraction of light speed. A missile of human size traveling at 95% the speed of light would carry energy equivalent to all of Earth's nuclear arsenals combined. Just a few of these missiles could guarantee the destruction of a targeted civilization, with even a single hit being potentially sufficient. This concept isn't far-fetched for a civilization slightly more advanced than ours. Such weapons are particularly dangerous because they strongly favor a first strike. Their incredible speed could render defense or countermeasures virtually impossible once launched. Interstellar conflict could be swift and decisive, with the initial aggressor often emerging victorious. This reality casts every civilization as a potential existential threat to others. In such a universe, there might only be two types of civilizations: those that remain silent and those that have been destroyed. What then is our course of action? For now, it's improbable that extraterrestrial civilizations have detected humanity. Our centuries' worth of radio signals have traveled a minuscule distance on a cosmic scale and have degraded into noise. At our current level of technology, staying unnoticed is likely if we don't actively seek attention, and if no one specifically targets our ordinary solar system. However, as we progress into space exploration, we must revisit these questions. We don't know if we are alone in this forest or not. For now, the wisest approach is cautious observation. If we observe another civilization revealing itself, our response should be deliberate and cautious, observing from a distance before engaging. Yet, perhaps our perspective is clouded by our primitive competitive instincts, which could be painting an overly fearful picture of predatory alien civilizations. It's possible that we, as a species, are not yet mature enough to view the universe correctly. There might be a friendly galaxy waiting for us. Be cautious with the signals we send into space, observe the skies, and learn more about our galactic forest. Whether this forest is fraught with danger, filled with allies, or completely devoid of other life, only meticulous observation and study will reveal the truth. Let's focus on that. In the clearing, the hunter finds himself face to face with another, both frozen in fear. Amidst this tense moment, he takes a deep breath and decides, maybe the way out of the dark forest is to step into the clearing together, choosing collaboration over conflict. How could the James Webb Space Telescope detect signs of alien life? Less than a year into its mission, the James Webb Space Telescope has already surpassed expectations. Its stunning captures of distant galaxies, nebulae, exoplanet atmospheres, and deep space fields are unparalleled in detail and sensitivity. Now, it embarks on one of its most thrilling tasks, the quest to find life beyond Earth. Using its advanced infrared capabilities, the Webb telescope will scrutinize distant worlds for chemical markers indicative of life and biological activity, known as biosignatures. This phase of its mission opens a new frontier in our understanding of the universe and our place within it. The Webb telescope could potentially detect signs of extraterrestrial life by using 4 distinct approaches. These include the identification of life-essential chemicals, substances indicative of biological processes, elements critical for maintaining a stable climate, and the occurrence of chemicals that typically do not coexist. In the search for life beyond our planet, the focus has been on studying terrestrial planets within their stars' habitable zones, where conditions might be right for liquid water. With advanced telescopes like Webb, equipped with sensitive optics and infrared imaging capabilities, the field is shifting from merely discovering exoplanets to a deeper analysis of their features. This advanced study involves directly imaging exoplanets and examining their atmospheres through spectroscopic data. Since the early 19th century, it has been known that specific chemicals absorb and emit light at unique wavelengths. Analyzing the chemical makeup of exoplanet atmospheres could provide more definitive assessments of their habitability. The Webb telescope is set to search for four primary chemical indicators: oxygen and ozone, phosphine and ammonia, methane and carbon dioxide, and chemical imbalances. Oxygen, for instance, is a significant biosignature due to its importance in life processes. Historically, Earth's atmosphere was rich in carbon dioxide, and the removal of oxygen created a reducing atmosphere, inhibiting oxidation. Over time, cyanobacteria and similar photosynthetic life forms transformed atmospheric carbon dioxide into oxygen gas, leading to the Great Oxygenation Event around 2.4 to 2.0 billion years ago. This transition from a reducing to an oxidizing atmosphere on Earth paved the way for the evolution and proliferation of more complex life forms, including insects, birds, mammals, and eventually hominins. Additionally, the interaction between oxygen gas and ultraviolet radiation in Earth's upper atmosphere resulted in the formation of ozone. The creation of the ozone layer was a pivotal moment, as it now shields life on Earth from most of the sun's harmful ultraviolet radiation. However, detecting these molecules in the atmosphere of an exoplanet doesn't automatically imply the existence of life. Various studies have shown that there are multiple non-biological methods, abiotic processes, through which a planet's atmosphere can become oxidizing and produce abiotic oxygen. Barstow notes another phenomenon, the runaway greenhouse effect, which occurs when evaporating surface water on a planet causes increased heating and further evaporation, creating a feedback loop. This process can result in significant amounts of water vapor in the atmosphere, which, when exposed to solar radiation, undergoes photolysis, breaking down into hydrogen and oxygen gases. The hydrogen may escape into space, leaving behind oxygen. In another scenario, planets tidally locked within their star's habitable zone can experience intense radiation on the side facing their star, leading to photolysis and an atmosphere rich in abiotic oxygen. Interestingly, oxygen gas, which is vital for many life forms, was toxic to the photosynthetic organisms that thrived in Earth's early history, suggesting that high oxygen levels could potentially hinder both naturally found in the atmospheres of gas giants and their icy moons are also produced by life on Earth. Phosphine, in particular, has recently garnered attention as a potential biosignature after its detection in Venus' atmosphere. However, both these gases are present in very small amounts on Earth, posing a challenge for their detection in the atmospheres of distant exoplanets. Methane and carbon dioxide are also considered potential signs of life, especially when found together, due to their biological origins on Earth. Animals produce both gases, with methane arising from organic decomposition and digestion processes, and carbon dioxide being a product of respiration in oxygen-consuming organisms. Additionally, carbon dioxide plays a crucial role in maintaining stable temperatures on a planet. An imbalance in its concentration can lead to extreme climate conditions like a runaway greenhouse effect or glaciation. Lastly, the existence of chemical imbalances in an exoplanet's atmosphere could be indicative of life. Life disrupts chemical equilibrium by consuming certain substances and producing energy and other byproducts. This concept aligns with the ideas of planetary scientist James Lovelock, co-founder of the Gaia hypothesis. In his work, particularly The Greening of Mars, Lovelock posited that true chemical stability is typically found in lifeless systems or planets, using Mars as an example to illustrate this point. Another potential biosignature not mentioned by Barstow is hydrogen. Recent research from Cornell University has revealed that volcanic hydrogen in an exoplanet's atmosphere might extend the habitable zones of stars. Hydrogen gas acts as a natural greenhouse gas, and volcanic activity is considered a crucial factor in the development of life. Further research from the University of Cambridge has introduced the concept of Hycean planets, ocean planets with hydrogen-dominated atmospheres, as prime candidates in the search for extraterrestrial life. Despite these findings, The presence of these chemicals in an exoplanet's atmosphere should not be interpreted as conclusive evidence of life. Barstow emphasizes the complexity and meticulous nature of exoplanet research. She points out that accurately measuring the quantities of these gases is challenging, as their signals can overlap and require careful separation for analysis. She underscores that the James Webb Space Telescope is just beginning to reveal a vast new field of planetary atmospheres. Through this exploration, many pre-existing assumptions about exoplanets and their atmospheres are likely to be revised or even disproven. Is it only a matter of time before we find alien life? The pursuit of discovering extraterrestrial life has shifted from questioning its existence to pondering when it will be found, reflecting a significant change in the focus of modern astronomy. There is a growing optimism among scientists that signs of life on distant worlds could be detected possibly within our lifetimes, with some even suggesting it could happen in the next few years. This heightened anticipation is bolstered by recent developments and missions in space exploration. For instance, the James Webb Space Telescope has provided encouraging signs of what could potentially be life on an exoplanet. This telescope, along with other missions, marks a new era in the space race, one that is now centered around making what could be one of the greatest scientific discoveries. The vastness of the universe, with its seemingly infinite number of stars and planets, leads to the logical assumption that Earth might not be the only place with intelligent life. Today's advanced technology and exploration capabilities have brought humanity to a pivotal point, where answering the profound question of whether we are alone in the cosmos is more possible than ever. This current phase in space exploration goes beyond just exploring the unknown. It's also about the quest to find life beyond our planet in the expansive universe. Telescopes are now capable of analyzing the atmospheres of distant exoplanets, searching for chemicals that are typically produced by detection of a gas on the exoplanet K218b, located 120 light-years away, which is similar to one produced by marine organisms on Earth. K218b is situated in the Goldilocks zone of its star, an area where conditions are just right for liquid water to exist, which is crucial for supporting life. Within a year, scientists expect to confirm whether these initial signs of life are valid. The lead researcher of this study from the Institute of Astronomy at Cambridge University expressed that a confirmation would dramatically change the approach to searching for extraterrestrial life, suggesting that life could be more common in the universe than previously thought. Even if signs of life are not found on K218b, there are 10 more planets in the Goldilocks zone to be examined, and each result, whether positive or negative, will offer valuable insights into the potential for life on these planets. This project is just one among many others aiming to find signs of life in the universe, some focusing within our solar system, while others look farther into deep space. The capabilities of telescopes like NASA's James Webb Space Telescope are impressive, yet they have limitations, particularly in detecting smaller, Earth-like planets close to their stars due to glare. To address this, NASA plans to launch the Habitable Worlds Observatory in the 2030s, equipped with technology to minimize starlight and analyze the atmospheres of Earth-like planets. Another significant development is the European Southern Observatory's extremely large telescope, which will be situated in the Chilean desert. Its large mirror will enable it to capture detailed observations of planetary atmospheres. These advanced telescopes utilize a centuries-old technique used by chemists to identify chemicals and materials based on the light they emit, allowing them to analyze the light from the atmospheres of planets hundreds of light-years away. In addition to exploring distant exoplanets, some missions focus on the icy moons of Jupiter and Saturn, which are considered promising locations for extraterrestrial life. NASA's Clipper and the European Space Agency's Jupiter Icy Moons Explorer missions are set to explore Europa, one of Jupiter's moons, in the early 2030s. Europa, with its subsurface ocean and water vapor plumes, is a prime candidate in the search for life. NASA is also sending the Dragonfly spacecraft to Titan, one of Saturn's moons, known for its carbon-rich chemicals and potential for supporting life. Meanwhile, Mars, though currently inhospitable, is believed to have been once capable of supporting life. NASA's Perseverance rover is collecting samples from a crater that was possibly an ancient river delta, with plans to return these samples to Earth for analysis in the 2030s. Beyond the solar system, the search for radio signals from alien worlds continues, led by institutions like the Search for Extraterrestrial Intelligence (SETI) Institute. The James Webb Space Telescope's ability to identify likely places for alien civilizations has refocused and energized SETI's search efforts, now utilizing advanced technology to detect potential communications from distant planets. While some scientists remain skeptical about the likelihood of receiving a clear signal from extraterrestrial life, the possibility remains an exciting and unambiguous method of confirming the existence of life beyond Earth. The past 3 decades have seen a revolution in our understanding of exoplanets, and the discovery of signs of life would be a monumental scientific breakthrough, altering humanity's perception of its place in the universe.